So, hello everyone. For today, uh, we have three topics to discuss, and the first topic is simple linear regression. So, let's move on with the example. So, example number one, an ice cream vendor wants to see how many ice cream he can sell in 6 days with varying weather temperature each day. So, here are our given values. So X represents the day of ice number of ice cream sold per day, and Y represents the weather temperature. So for this specific topic, we need to get the summation of X, the summation of Y, the summation of X squared, and the summation of X times Y. So for our solution, we need to get A and B. So here you can see the solution for A, which is summation of Y times summation of x squared minus summation of x times summation of xy all over n times summation of x squared minus summation of x squared. And then we have b, which is n times summation of x squared, x times y minus summation of x times summation of y all over n times summation of x squared minus summation of x squared. So on our right hand side, we plug in the values, and then for A we get negative 8.916, and then for B we get 0.642, and then we just have to plug this in our regression equation, which is y prime is equivalent to A plus bx, and our final answer is y prime is equivalent to negative 8.916 plus 0.642x. So for our second topic, we have hypothesis test in simple linear regression. So we will be relating this topic in our previous example. So for example 2, an ice cream vendor wants to see how many ice cream he can sell in 6 days with varying weather temperature each day. So first, we have to state the null and alternate hypothesis. So for our null, we have beta is equivalent to 0, and our alternative is beta is not equivalent to 0. So what this means is if beta has if beta corresponds or has a relationship with the given data. So to get value of t, we get our significant value, which is 0.05, and since our beta is not equivalent to 0, it means that it is a two-tailed test, so we have to divide it by 2. So it has to be 0.025, and then our degree of freedom is n minus 2. So 6 minus 2 is equivalent to 4, and our value for t is 2.776. So for our solution, we have our linear regression equation again. So y prime is equivalent to negative 8.916 plus 0.642x. So now we have to get beta sub 1, which is sum of squares xy over sum of squares xx, and we have our equation here. So plugging in the values, we have 11,051 minus 179 times 362 all over 6 all over 22,232 minus 362 squared all over 6, and that is equal to 0.642. So we have our sum of squares values here on top. So for xy we have 251.333, for XX, we have 391.333. And then for YY, we have 164.833. So now we need to get SSE. So it's equal to sum of squares YY minus B hat sub 1 times sum of squares XY. So plugging in the values, we have 164.833 minus 0.642 times 251.333, and we will get 2.723. And then we also have to get the value of S and the value of S sub B hat sub 1. So we have our values here. We have 0.825 and we have 0.042. So for our test statistic, we also have to solve for it, and we have B beta sub 1 all over S S sub beta sub 1. So plugging in the values, our final answer is 15.286. And then to get the value of the critical value of T, we have alpha is equivalent to 0.25 and our degrees of freedom is 4. So looking at the table, that will lead us to 2.776. So it's a two-tailed test, and then as we can see here, the value that we got is within the rejection region. So in conclusion, we reject the null hypothesis and accept the alternative hypothesis, which means that there is enough evidence to prove that the weather has an impact on the sales of ice cream. So for our third and final example or topic, we have confidence intervals on slope, intercept, and mean response. So a professor at a high school is interested in the relationship between hours spent studying for a short quiz and the scores that are attained with it. She randomly selects 12 students in her class and records their recent short quiz scores. And she asks each of those 12 random students how many hours they spent studying for the quiz. So shown in the next slide is a computer output from the least squares regression analysis on her sample. So we have this table here. So we have the predictor, coefficient, standard error of coefficient, T, and P. So assuming that all conditions for inference have been met, what is the 95% confidence interval for the slope of the least squares regression line? So this is what the graph looks like. So as you can see, we have 12 dots here, which correspond to the score and the time spent of each student, and the slope is 2.331. So for our solution, we have the coefficient grade plus minus the t value, which is 0.95, and then our degrees of freedom is 10 since n minus 2, and then our n is 12, so 12 minus 2 is 10, and then we multiply that by the standard error coefficient grade. So plugging in the values, we have 0.138 plus minus 2.228 times 0.043, and then our final answer is 0.0423 less than or equal to beta sub 1 less than or equal to 0.2338.
Hello everyone, good day. So we have here is lesson 10, simple linear regression and correlation. We have topic 4, prediction of new observations. So, a local pet store wants to predict its monthly revenue based on the number of pet food bags sold per month. They have collected data for the past 6 months as follows. For the first month, they have 100 pet food bags, then 35. Second month, 120, 4,000. Third month, 140, 48. Fourth month, 160, 52. Fifth month, 180, 61. Sixth month, 200, 68. And then using this data, our task is to predict the pet store's monthly revenue if they sell 150 pet food bags in a month. So, step 1 is to find the mean of X and Y. So, in this step, we want to find the average number of pet food bags sold and the average monthly revenue. To do this, we add all the values in each column and then divide by the number of months, 6 in this case. So, we have 900 divided by 6 kasi X bar yung hinahanap, then we will have 150. And then, for the Y bar naman, we have, yan, 3,500, 4,000, yan, i-add yan lahat. So, over 6 din ulit. We have 30,400 divided by 6. We have 5,066.67. For step 2, calculate the slope B of the regression line. Ayan yung gagamitin nating formula. So, the slope is a measure of how steep the regression line is. To find the slope, we need to compute some intermediate values. Ayan. Ayan yung mga kailangan nating values. Ayan, X minus X bar, Y minus Y bar. The differences between each X value and the mean of X times X minus X bar. Ayan, mga ganon. Ayan, ayan guys. Ayan yung kailangan nating hanapin. So, sa column na to, ayan yung mga kailangan nating hanapin. Ito yung 6 months. So, yan, may mga negative values. Ayan. Kasi, gagamitin natin yung 150. So, bali, minus 150 siya dun sa kanina. So, 100 minus 150, kaya naging negative 150 yan. So, tapos 120 minus negative 150, naging negative 30. So, ayun. Yun. Ganun-ganun lang ulit yung formula. Tapos, 140 minus 150, ayan. Negative 10. Ayan. Yan. Tapos, dito naman, sa kabila, Y minus Y bar, gagamitin natin 5,066.67. Yan. Negative 5,066.67. Yan. Sulat lang natin para hindi tayo malito. So, ayun, tignan natin yung monthly revenue Y in USD doon sa taas. Yan yung magiging answer. Tapos ito naman, ipagta-times mo lang yung dalawa. Yan yung magiging answer. So, yan yung product nitong dalawang column na ito. X minus X bar tsaka Y minus Y bar. Ayan. Yan. So, dito naman is squared mo lang yung unang column, ay dito yung sa kasunod ng month, yung column na yan, X minus X bar, squared lang yan. So, negative 50 squared, 25 yun. Yun, ganun-ganun lang din sa iba. So, ngayon, sum yan na natin lahat. We have 7,000. Nakuha na natin, guys. Ngayon, compute the slope B. Ayan, mayroon tayong 29.29. So, yung calculate the y-intercept of the regression line, ayan. Formula lang din yan. We get, ayan. Next is write the linear regression equation. Ayun. And then, step 5, predict the monthly revenue for 150 pet food bags sold. Ayan. Yan yung ating nakuha. So, ang prediction natin dito, Now that we have the linear regression equation, we can use it to make predictions. To estimate the monthly revenue for selling 150 pet food bags, we plug in x equals 150 into the equation and calculate the corresponding y value. This gives us the predicted revenue for that month. So y is equal 673.17 plus 29.29 times 150 equals 673.17 plus 4393.50. Nakakuha tayo ng 5,066.67. So, remember, this is just an estimate based on the given data and a simple linear regression model. Actual revenue may vary due to the other factors not considered in this model. For lesson 5, we have adequacy of the regression model. We have here the problem that a local bike rental shop wants to investigate the relationship between the daily temperature X and the number of bikes rented Y. They have collected data for 7 days as follows. Ayan, we have day 1, 60, 42, day 2, 65, 50, day 3, 70, 54, day 4, 75, 60, day 5, 80, 80, day 6, 85, 95, day 7, 90, 98. So our task is to calculate the correlation coefficient and interpret the adequacy of the regression model. So for step 1, we need to compute the mean of X and Y again. So in this step, we find the average daily temperature and the average number of bikes rented. To do this, we add all up the values in each column and then divide by the number of days. Yan. So, for temperature, we add yan. Lahat yan. Then, we get 75. And then, for the mean of Y naman, we have 487 divided by 7 is equals to 69.57. There. For step 2, we calculate the correlation coefficient or the R. We have here the formula. So, the correlation coefficient measures the strength and the direction of the linear relationship between two variables. In this case, temperature and bikes rented. So, ayan. We have this table right here. So, ayan, inayos lang natin yung formula kasi gumulo-gulo kanina. The value of R can range from negative 1 to 1. A value of 0 indicates no linear relationship. So, to calculate R, we need to compute some intermediate values again. Ayan, yung X minus X bar. Ayan. Y minus Y bar, X minus X bar times Y minus Y bar. Ayan. Ganon ulit, same sa lesson 4. So, yan, gagamitin lang natin yung 75, our mean of X. Yan, maglalagay tayo dito ng solution. So, we have 60 minus 75, we get 15. So, ayan. The mean of X is 75. We just need to subtract that. Ayan. Same goes with Y minus Y bar. Our mean of Y is 69.57. So, we need to subtract that in 42. Kunyari, 42 sa bike rented ha. 42 minus 69.57, we get 27.57. So, ganun siya guys. That's how it goes. So, here naman, just get the product of those two columns. So, pag tinimes mo yung dalawa, we get 413.55. Yung X minus X bar tsaka Y minus Y bar. This one naman, squared lang siya ulit nung column na X minus X bar. So, dito naman, naglagay na tayo ng panibagong column. Lalagay na natin yung squared ng Y minus mean of Y. Ayan. So, now, we have 2951.24 and then we get, using the formula, 0.983. And then for step 3 is to interpret the correlation coefficient na. And then, The correlation coefficient are ranges from -1 to 1. In this case, the correlation coefficient is approximately 0.983. This value is close to 1, which indicates a strong positive linear relationship between daily temperature and the number of bikes rented. As the temperature increases, the number of bikes rented is also increasing. Since the correlation coefficient is close to 1, that the linear regression model is likely to be adequate for describing the relationship between daily temperature and the number of bikes rented. The strong positive correlation suggests that the regression model will have good predictive performance for this particular dataset. Keep in mind that the correlation does not imply causation, and the other factors not considered in this model could also influence the number of bikes rented. Moreover, the correlation coefficient is sensitive to outliers, so it's essential to verify the data and ensure that there are no extreme values that may be affecting the result. So for topic 6, we have the transformation to linear regression. So we have a problem that a local farmer notices that the growth of their apple tree seems to be related to the age of the trees in a non-linear fashion. They have collected data for 5 trees as follows. So we have the age and the growth. Yan, in meters. Ayan. The 6.0, ayan. By looking at the data, the farmer suspects that the relationship between age and growth might be quadratic. Perform a transformation to fit a linear regression model and find the equation of the transformed model. So, step 1 is to transform the data. Ayan. In this step, we will transform the data to make it suitable for a linear regression model. Since we suspect that the relationship between the age of the trees and their growth is quadratic, we'll create a new variable by squaring the age of the old trees, and this new variable z will be used in the next step to fit a linear regression model. Ayan, since the farmer suspects a quadratic relationship, we'll use a square transformation. Create a new variable z by squaring the age x. Ayan. 1 squared, 2 squared, ayan. 3 squared, we have 9. 4 squared, 16. 5 squared, 25. Ayan. Yan yung sagot dito sa ating z. So, step 2 is to perform a simple linear regression using the transformed data. Now that we have the transformed data, we can now perform a simple linear regression. First, we find the average of the squared ages and the average growth. Next, we compute some intermediate values, like the differences between each z value and the mean of z times z minus z square bar. Ayan. We need to compute the slope b. So, we have this table. Ang gagamitin nating z is 11, mean of z. So, ayan, 11. So, 10 ay 1 minus 11. Ayan, 10 yung magiging answer. So, ganun din yung gagawin natin sa y. We have 2.76. Ayan yung magiging answer. So, ito, product siya. Sorry, product, hindi sum. Product yan ng dalawang column right here. So, ngayon, z minus z bar, squared mo lang to. Yan, negative 100 squared, negative 10 squared, we have 100. Ayan, yan lang yan. So, yan. Now, the sum, we have 374. Ayan, yung magiging answer. So, compute the slope B. We get 0.227 and compute the y-intercept, we get 0.237. So, now, step 3 is to write the linear regression equation for the transformed data. So, once we have the slope B and the y-intercept for the transformed data, we can now write the linear regression equation. Ayan. So, for step 4, convert the transformed equation back to the original variables. Now that we have the linear regression equation for the transformed data, we need to convert it back to the original variables. Since we use the square transformation, we can replace z with x squared into the equation to get the quadratic regression. Ayan. Keep in mind that this is just an estimation. Yan. Based on the given data, quadratic regression model. The actual growth may vary due to the other factors not considered in these models. Also remember that the transformation we use in this problem is just one example. There are many other types of transformations that can be applied depending on the specific relationship between the variables.
Hello everyone, this is our problem set 3 and I'm here to talk about multiple linear regression. So for my first topic, we have the multiple linear regression model. So here we have our first problem. Suppose we have the following data set with one response variable y and two predictor variables x1 and x2. So given in the screen is the table we're using. For the first observation, y is equals to 140, x1 is equal to 60, x2 equals 22. Next is 155 for the y, 62 for the x1, 25 for x2, 159 for the y, 67 for x1, 24 for x2, and so on and so forth. So for our problem, we have here our solution. So we start with our initial table from the previous slide, and we compute for their mean and the sum. And once we compute for the mean and the sum, we create another table, which is for x1 squared, x2 squared, x1y, x2y, and x1, x2. And then we compute for their sum. And the formulas on the right are the formulas that we are going to need to arrive at our final conclusion. So we have the summation of x1 squared, which is summation of x1 squared minus the summation of x1 then squared all over n. Then followed by same formula for x2 squared. Then we have x1y. Summation of x1y is equivalent to summation of x1y minus summation of x1 times summation of y all over n. Similar formula for x2y. Then summation of x1 x2 is equals to summation of x1 x2 minus summation of x1 times summation of x2 all over n. Then we have the formula for b1, which are given on screen, similar to b2, with the b sub 0 equals y multiplied by b1 minus b1 times x1 minus b2 times x2. And then finally our y equals to b sub 0 plus b sub 1 times x1 plus b sub 2 times x2. So here we have our computation for our givens earlier. So we have x1 squared is equals to 38,767, which is the sum for x1, minus 555 squared all over 8, giving us a value of 263.875. Summation of x2 squared is equals to 2,823 minus 145 squared all over 8, gives us 194.875. Summation of x1y is equals to 101,895 minus 555 times 1452 all over 8 gives us 1,162.5. Summation of x2y gives us the final value of negative 953.5. Summation of x1 x2 gives us negative 200.375. And then using the given values above, we then compute for b1, which will then give us 3.148. b2, which gives us negative 1.656. And b sub 0, which is negative 6.867. So we have the solution here on the other side, which is the regular sums, which we have all the values from summation of x1s all over to summation of x1, x2. which would then give us the last values of b1, b2, b sub 0, and the final solution, which is y equals negative 6.867 plus 3.148 x1 minus 1.656 x2. So the meaning of this is, for v sub 0, which is negative 6.867, when both predictor variables are equal to 0, the mean value for y is negative 6.867. For b1, 3.148, a 1-unit increase in x1 is associated with a 3.148 unit increase in y on average, and assuming that the x2 is constant. And lastly, b2 is equals to negative 1.656. A 1-unit increase in x2 is associated with a 1.656 unit decrease, since it's negative, in y on average, assuming x1 is held constant. So for our next problem, we have multiple linear regression, hypothesis test, and for here we have a simple ANOVA problem, which will then help us to test our hypothesis. So problem states to consider the following samples. Test the hypothesis that the population means are equal against the alternative hypothesis that at least one mean is different from the other two. Use 0.05 level of significance. So here we have 3 samples, sample 1, sample 2, and sample 3. Sample 1 has 3 values, sample 2 has 4, and sample 3 has 3. So for sample 1, we have 3.1, 4.4, 1.2. For sample 2, we have 5.4, 3.6, 4.0, and 2.9. Lastly, sample 3 has 1.1, 0.2, and 3.0. So for this problem, we are going to use the solution, the formula, f equals mst over mse, mst equals sst all over k minus 1, mse equals sse all over n minus k, and the other formulas for TSS, SSTs, and SSEs. So to compute for our problem, we have the original table, sample 1, sample 2, sample 3. We then compute for their sum and their average. So sample 1 sum is 8.7, sample 2 sum is 15.9, and sample 3 sum is 4.3. Sample 1's average is 2.9, sample 2's average is 3.975, and sample 3's average is 1.433. So to compute for the y, which is, we use the formula summation of all the sums all over n, which is our number of values. So here we have 8.7 plus 15.9 plus 4.3 all over 3 samples in sample 1, plus 4 samples in sample 2, and 3 values from sample 3, which will yield us a y value of 2.89. For the SST, we use the formula the number of values multiplied by the average minus y. So for sample 1, we have 3 values multiplied by 2.9, sample 1's average, minus 2.89, which is our y, plus 4, sample 2's number of values, multiplied by 3.975, which is the average of sample 2, minus y, or 2.79 squared, plus, lastly, sample 3 has 3 values, 3, multiplied by the average, 1.433, minus our y, 2.89 squared, gives us a SST value of 11.077. TSS is an individual summary of given values minus our y squared. So we have 3.1 minus 2.89 squared, which is sample 1's first value, plus 4.4 minus 2.89, then all the way up to our last value in sample 3, which is 3.0 minus 2.89 squared, will give us a TSS value of 2.367. And lastly, our SSE, which is TSS minus SST, which is 23.67 minus 11.077, will then gives us 12.593. For MST, it's just SST all over our number of samples, which is sample 1, sample 2, sample 3 minus 1. So since we have 3 samples minus 1 all over 2. So we have 11.077 all over 2 gives us an MST value of 5.539. Lastly, MSE, we have our TSS value all over n minus k, which is this one. Since we have 10 values, minus 1, and then minus 10 values minus the number of samples. So we have 10 values minus 3 gives us 7, which will then give us an MSE value of 1.799. And using the formula for F ratio, MST minus MSE, MST all over MSE will give us a value of 3.079. So this is a tabular representation. So we have degrees of freedom. Treatment is, we have 3 treatments, 3 samples, minus 1 gives us 2. Our error is 10 samples, 10 values minus the number of treatments, which is 3, gives us 7. Then we just add all that up in total. So our sum of squares were given in the other table. Then using division, we then come up with the F ratio. And our F calculated is 3.079, while our F theoretical using the F table, we have 4.74. Since F calc is less than our F theoretical, we then fail to reject our null hypothesis HO. Now, lastly, for multiple linear regression, we have the prediction of new observations. So for the problem, it says, suppose the engineer wishes to construct at 95% precision prediction interval on the wire bond pole strength, where the wire strength x1 is equals to 8, the die height is x2 275, x prime is a matrix of 1, 8, 275, and the point estimate of pole strength is y sub 0 equals 27.66. And x sub 0 prime multiplied by x prime x times x sub 0 will give us 0.04444. So for our prediction of new observations, we have a formula below, which will then gives us the prediction interval. So we have y sub y0 equals to y0 prime times our beta. And then to compute for our prediction interval, we have y sub 0 minus t alpha over 2 n minus p, square root of the variance squared, multiplied by 1 plus x sub 0 xx is to negative 1, which is the adjoint, times x sub 0, and then the other one is vice versa. So to compute for this, we already have a given for most of our problems. So it's y sub 0 equals to 27.66. Our t at 0, 0.25, and 22, we have 2.074. Our variance, which is 5.2352. And lastly, our final value, which is 0.0444. So we just plug it in using the confidence interval solution, and we come up with 27.66 positive negative 2.074 square root of 5.2352 multiplied by 1 plus 0.0444, which will give us two values, 22.81 greater than equal y sub 0 greater than equal 32.51. So that gives us our final prediction interval for our new observations.
Good day, everyone. Right now, I will be discussing lesson 12, which is the design and analysis of single-factor experiments. So in a single-factor experiment with a completely randomized design, you'll see here that the levels of the factor are randomly assigned to the experimental units. However, we can also say that the experimental units are randomly assigned as well to the different levels of the factor. And you'll also see that there is no structure among the experimental units. So let's continue to our example. There is an investigation on how synthetic fibers are formulated which are used in the cloth. corresponds to tensile strength, or in other words, the strength of the fiber. An investigator wants to identify the best level percentage of cotton in order to determine the best or highest tensile fiber strength. Hence, the single quantitative factor will be the cotton percentage combined with the synthetic fibers. So here we will have 5 different treatment levels, and this will be evenly spaced from 20 to 40%, and each will have 5 observations, and the figure 1.0 will show the following. So in here, figure 1.0, I just put some observations for each percentage and plug this into Excel, and I also got its individual total and average. I also got the grand total and average here. And for the data, I made it so that there's an increase in strength as the cotton percentage is increased. However, in the 40% weight percentage, there's a sudden drop in the values. So by conducting an analysis of variance or data analysis in Excel, we can obtain the values such as our sum of squares, mean squares, f-value, and minimum. So in figure 2.0, I already made this in Excel, and now I will show you how this is done. So to do data analysis, we have to make sure that we have the toolkit needed. So you just go to options and general, options and add-ins, then Excel add-ins, then we press go, and then make sure that the analysis toolpath is ticked. After that, we will see the data analysis here under data. Just click on it, then we do ANOVA single factor. Then our input range will be these values, the y values, the observations. Then since it is grouped by rows, I made it in rows, then you just click group by rows. And after that, you'll end up with these values: RSS, degrees of freedom, MS, and many more. So from that, we can now test the hypothesis, or we can now indicate a hypothesis. So our HO, our null hypothesis, is that there is no difference in cotton percentage, and for our alternate, then there is a difference. The cotton percentage does make a difference. So for our hypothesis testing, we have to find our F value based on the F table. So our degrees of freedom associated with treatments will be A minus 1, which is 5 minus 1 equal to 4. And for the DOF associated with error, it will be A times N minus 1, which is 5 times 4 is 20. Then our F value, our alpha, is 0.05. Then our A minus 1 is 4. Then A times N minus 1 is 20. Then we just find this in the F table. Then we end up with 2.87. Then we just compare the value of the F that we got from the Excel, which is 71.39, and we see that it's significantly greater than 2.87. So this means that we can reject the null hypothesis in favor of the alternate hypothesis that the cotton percentage does make a difference in the tensile strength of the fiber. For the confidence intervals on the mean of the ith treatment, we can find this through this formula. So for a y bar, we can access this through Minitab, through its analysis of variance output. And for t, we just do the same. We do with this formula, the alpha over 2 times and the a times n minus 1. So we get 0.025 and 20, and we get the t value of 2.086. Our MSE will be this one, 1.8. Then our n is equal to 5. For confidence intervals and the difference in two treatment means, we do this formula, then it basically uses the same values. Then for the multiple comparisons following the ANOVA, the Fisher's least significant difference, or the LSD, can be used. So same here, we have same values that are needed. Then when we plug and compute the values, we end up with 1.77. So this means that if the averages of any two treatments differ by more than 1.77, this entails that the same pair of treatment means are different. Moreover, for residual analysis and model checking, the residual values, which are obtained by getting the difference between each observation and the average of each percentage, which is these averages. Then this can be used to generate the normal probability plots, the plots of residuals versus factor levels, and the plots of residuals versus the y bar. So that's it. Good day, everyone. Right now, I will be talking about the second topic under the design and analysis of single factor experiments, and this will be the DOE using randomized complete block design. So before we get into the example, let's discuss what the randomized complete block design is. So the randomized complete block design basically differs from the completely randomized design, wherein the experimental units are now grouped into blocks, where these blocks, they isolate the known variation. So likewise, the treatment combinations are assigned randomly to the experimental units within the block. So now that we know that, let's go on to our example. A school wanted to test different bus tires from 4 different tire manufacturers to test and identify the tire wear from each company. You can only place 4 tires in a bus, but you have a sample of 6 tires from each manufacturer. Therefore, use a randomized complete block design, or RCBD, and test 1 tire from each manufacturer once, in random order on every bus. The data are shown in figure 7.0. So I already, I said, I put the data in Excel, wherein we have the treatment and the box, which is the buses, and these responses, they all represent the tire wear in millimeters. So similar to the first topic, by conducting an analysis of variance through data analysis in Excel, we can obtain the sum of squares, the mean squares, the F value, and many more. So once again, I already did the data analysis in Excel, but instead of using ANOVA single factor, we now do ANOVA two factor without replication. So if you go here, just do data analysis, click ANOVA two factor without replication. Then our input range will be these. Then now we can put labels, since we included the labels. And you'll get these values. Then we can move on to our hypothesis testing. So similar once again to the first topic, the single factor experiment, the completely randomized single factor experiment. Our hypothesis stays the same. Our null is it doesn't make a difference, or that the tire type does not have an effect on the wear, while our alternate is that the tire type does have an effect on the wear. So we can do the same strategy wherein we compare the calculated F value and compare it to the 3.76 that we got from the ANOVA, similar to what we did in the first topic. However, if we look at the p-value here, the p-value is 0.033994. So for our hypothesis testing, rather than doing the comparison of the F values, since our p-value is very small and it's less than 0.05, then we can say that the result is statistically significant and that the null hypothesis may be rejected because it's less than 0.05. So the null can be rejected in favor of the alternate hypothesis, wherein the tire type does have an effect on the wear. So that's basically about it. And also in the ANOVA table, there will be values for the F, the p-value, and the F crit under the row columns, the blocks and buses. However, we don't need those, so we just simply remove them. So that's about it. Thank you.